you need to fix the number of the particles. So this is the fixed number. But we have one extra condition here, that we are looking for more possibility. The possibility is that after the energy, when we fix it, will we have a control parameter to control the average of the energy. Is it possible at the same time to control the average of the number of the particle in each energy state or not? Average of the number of the particles which seated in each energy state or not? For example, look at that. Again, we have a 3 energy state, for example, E1, E2. And we have the number of the particle, I don't know, 10 million, 1 million particles. That's it. I know this is a very... okay, how you can... And my idea is that to keep the average of the energy always, for example, in some given numbers, fix it. So this counting problem, we know how to do that. You needed just to substitute, and this is a big number. You can just substitute some numbers here, some number, and always check that is it sigma E R N R E or not. This is your control equations. You need to check. But I add one more thing. I want to ask you that can you at the same time control for me that the average number of the particle which will sit in one of these energy states or not? For example, for one configuration, for one energy, you can have 15 particles here, okay, and the rest other one. In the second energy, you needed to put 10 particles here because you don't need this energy level. This energy level will be important. The other particle will be sitting, and then the other ones, again, this energy level will be important. 1,000 particles will be sit here, and the other one will be sitting. At the final, you can say that this energy state, in average, was occupied by the average number of the particles. Yes. At the first energy, it was occupied by 50 particles. After the second part, it's 100 particles, or 10,000 particles. So at the average, you can talk about the average of the number of the particles. For example, occupied the energy stated in E1, for example. You remember, because I give you different energy. You have a different energy. I give you, if you remember, the example was that I give you a list of the energy. I say that just arrange the particle to sit in this to get this energy. So for each energy which I gave you, which I gave you, then this state will be occupied by some numbers. For example, if N1, if you put it En1 with 10, for example, the second one, N1 again, N1 will be with different energy, for example. At the final, when the system reach the equilibrium, you can say that, okay, at the average, how many particles was occupied or was sitting in the energy level 1. You just make it this average. It looks very easy, so you don't think that you needed these equations. Well, we needed that because, as you know, we are talking about the ensemble, so you don't have a 3 energy level. You have some systems in the number of the Avogadros, and each system have a different energy level, like 1 million hydrogen atom. So you see that that's not possible to easily distribute the particle between them. So that was the idea. We use the factorial. Okay, this equation is that. It looks not very friendly because this you understand how this will get, you will get the average But this is also not very hard to understand, you know. You want the average of the energy, so average of energy is just multiply the number of the particles sitting at the spatial energy. No? So if I ask you average of the number of the particles, you can say that just I multiply the number of the particles sitting in the spatial in the given number, the given numbers. For example, if you take the energy level E1, for example, here, so this will be the number of the particle which in each time seated in the energy level of E1. R is the index for the energy, and S is the number for index for the particle. For example, you see here, that was the. Actually, if I want to write this, when you occupy the system, when energy E1, the number of the particles seated here was, for example, 10. When I occupy the system with energy E2, N1, E2 is still in the 1 was 100. So you see that you needed two index. One refer to the N1 or N2 or N3, the number of the particles sit in each box or each element, and the one you needed for the energy. So this index is related to the energy. So, okay, to find the N or the S is not hard, so we use that. Variation of the logarithm W N or S you introduce it again, the Legendre multiplier multiplicities, Legendre multiplicities. For each constant, you need to introduce one Legendre constant, Legendre multiplier. Minus sigma n s r and s minus gamma, yes. That's will be zero. Yes.
Even for energy, we need the NRS. It is not related only on R for energy, or not? Beta summation of E R.
Yes, but no. You see, I told you have two things. One is the number, the average of the number of particles sitting in energy state, and one is that in each energy, some particles sit in this energy state. I mean, if you forget about what average I told you, I said that energy is E1, 10 particles will sit here. How you can write that? You can write that this N1 is equal to 10. Yeah, you guess like that. But next time when you change